Good morning to all of you. So, so, day before yesterday, we started learning about the pulse technique and pulse technique in the NMR. And I told you initially we can take to understand this concept, we can take the analogy of a hammer striking the bell. So that kind of thing we imagined. So when a hammer strikes the bell, it vibrates at all the character. The sound that you hear, the clang that you hear, is a result of several waves, the oscillations that take place. So there are one, two, three different modes of oscillations taking place simultaneously, and that is appears for a short duration to you. That is a pulse. So that kind of thing is what we are going to do, a mixture of two three waves at which the given species can oscillate with characteristic frequencies so that is a pulse mixture of several waves, different waves, okay, together and applied for very short duration. So usually, so this is what the example was, and we started off from here, and I think it is available. I'll make it available on YouTube for previous class lecture as well. So now moving ahead, if so yeah, in the context, putting in the context of NMR, how we what we learned here is that earlier we were using initial description. I told you that we apply a magnetic field, the precession starts, and there is a radio frequency field which usually kept fixed. That's the early model that we had, and that fixed radio waves is incident upon that an absorption occurs. So that was being analyzed in previous cases. So at what point resonance condition is achieved, if there might, because of the change electronic environment, the resonance will occur at different magnetic fields, and so you had to keep adjusting the magnetic field. So to enable, you were scanning this magnetic field earlier. In this particular one, we are not going to do that in this, and we are not going to scan anything, not neither the field nor the radio waves. Okay, we are keeping giving. So what we'll do, I'll just tell you. Uh, so we use a pulse. A magnetic field is applied. A pulse is used. A pulse of NMR. Sorry, the radio waves. So a pulse is a mixture of several such waves put together, and just एक बार में सबको थ्रो कर दिया आपने उसके सैंपल के ऊपर. So applied field B naught, then apply the radio frequency wave, and the radio frequency that you are applying, radio waves that you are applying, is a circularly polarized wave. In this, in a pulse technique, what you do, and so the pulse, whenever there will be absorption or anything, the pulse profile will change, and so that change in the pulse profile, if you are able to analyze that, you will get all the information inherent in the system. So that is the idea, and for that analysis part you will require Fourier transformation, a mathematical step which will deconvolute, which will all the such waves, frequencies which were together in a mixed complicated pulse, which was appearing in a complicated profile of the pulse. uh, so that's where we need the algorithm, we need the Fourier transformation to do that. So that is something the computer does nowadays. You write a program, mathematical program, feed it into the system, and it will, after the pulse has been acquired, you have been able to. So this is what is normally done in the modern setup of NMR. Yeah. So that is what I told you. It is what we do is equivalent of the hammer blow on the bell. Okay, so these are things basic, very fundamental that we try to understand. You already know these things. This is the vector and spin angular momentum vector, and this is the z component represented through this along this lying along the z-axis. So this is the z component of the same vector. Okay, ms h cross or mi h cross you can write. Yeah, this is already discussed last time. So this is what happens. You have initially when no field, you you have the population of alpha state, beta state, both are equal. So you have 100 nuclei, 50 of them will be in alpha state having ms plus half spin, or and other 50%, 50 nuclei out of 100 would be having the beta state. Both are equal in energy when there is no magnetic field. And here in the second picture what we have, you apply a static magnetic field B naught. Most of the spins in the nuclei would like to align. So you see the population has changed now. There are more of alpha than the beta, and so there is if you calculate the net summation of these all magnetic moments, you will get a net magnetization as this pointing in the direction like this, and it will start precessing. It will start moving along the cone, this cone that has been shown, this upper circle that you are seeing. So that is a precessional motion that sets up, and this the radio frequency that we are talking about now we are going to apply is rotating at the same. So mu L is the Larmor frequency, precessional frequency, and we apply a radio wave. Uh, if we apply a radio wave having mu frequency mu such that mu is equal to mu L, Larmor precessional frequency, then situation becomes very interesting, and what we are going to do, yeah, learning this thing is, yeah, will help you. So this is the picture of what we visualize as a circularly polarized wave, electromagnetic wave. So this is the direction of propagation, z, and this is the xy plane circle xy, and you can see that the magnetic field vector is contained in the xy plane. It is moving in the circle in the xy plane, magnetic field vector, which is perpendicular to the direction of propagation of the light. So imagine that this is what is going to happen. We are having mu L, the net magnetization vector capital M is precessing around in this cone, and then we apply a radio frequency wave, radio wave, which is having the oscillation similar to the same as the precessional frequency. So this is the situation. So that vector, that magnetic field vector is, so this is the, so static magnetic field applied B naught first. This is what we do. This precession starts now of the net magnetization that we are having. The vector representing the net magnetization is, it starts moving in this circle that we see here. Okay, the arrow starts precessing around along this cone. Now when you apply radio wave, radio wave of frequency mu and mu l, such that the frequency of this radio wave is equal to the mu l, the frequency of precessional frequency. So as I told you, the wave is circularly polarized and so if the direction of radio frequency wave is this, the vector, the oscillating magnetic field vector, is restricted to this xy plane. It is oscillating in a circle, kind of circle. It is moving in a circle in the xy plane, and that's how we visualize. And that vector, from the radio wave, this b1 that we are writing is the magnetic field vector, magnetic field vector oscillate, in fact the oscillating magnetic field vector in the radio wave, right? So this is what we are picturing right now. And I also told you that now this is the what we view from outside. If you are viewing from outside, this is the thing that it will appear to you that both are moving in circles, the b1 vector moving in circle, the lower circle, the upper magnetization vector, both are moving at a certain speed, at an equal speed rather. The upper the magnet capital M and the b1 both are moving in the circle xy plane, okay, one that is represented by the upper circle and the one by the lower circle. So this is for an observer who is outside this system, he is sitting in the laboratory and observing the things. Now think of it that the observer happens to be on this circle, the lower circle that it is, if you are sitting on this circle and something, so observer is here, okay, on this circle, so and moving at the same speed as this. So what will appear to you, the b1 will be appear to you as static, the magnetization vector capital M appears. So this is what we mean by having a rotating frame. So stepping on to a new system, rotating frame of reference. So change of frames from a laboratory frame to a rotating frame. Then what appears to me is that B1 rotating frame of reference. So it is whether something is moving or not, and what is the speed. It is all it depends. It depends on the frame of reference, right? So it is similar to a situation that two cars are moving at the same speed. You are standing beside on the roadside, and you observe that two are moving at a speed of 100 kilometers per hour simultaneously. But suppose you as an observer now sitting in one of those cars and then observe the other car which is moving at the same speed, you will see that it is not at all moving. You will find that it is static. So it is the frame of reference when it is changed. So we step on from a laboratory frame, static frame, to a rotating frame of reference, as I told you, as pictured over there. Then the b1 appears static, the M, the vector that is that also appears static, uh, and then we visualize it as what happens like this. Yeah, so this is the picture, you understand. Red one is your, now red one was the magnetization vector. So see, green one is the b1, and the radio frequency when it is applied, so only b0 is applied, and as the green one comes, you see the radio frequency is applied, circularly polarized one, and the green one is from a rotating frame, it appears static. The green thing is that. So the oscillating field vector B1 appears static from a reference frame of rotating frame. Okay, and along that B1 you have this moving thing. Okay, so this happens. So this was um, what was this? This was V naught, the blue one. This is your M, and this one your B1. This is what we were talking about. So there is another precision that is now set up when we are looking from the reference frame, or when we apply a circularly polarized electromagnetic wave, the radio wave. Okay, along the same line. So we light is moving. This is the direction, uh, radio wave direction of travel. Okay, and in the xy plane you have this oscillation of b1 vector happening, and this b1 is the green one that appears static like this. And so this tipping of the, so when the b1 appears, so b1 is static and you apply so magnetic field, and around that the precessional motion will start. So this precessional motion that we are talking about is represented in this picture as well. Sorry. Okay. So the B1 appears stationary. Magnetization M appears stationary if you are viewing it from a rotating frame of reference. And this is so this becomes convenient when we change the frame of reference. Your mathematics, your understanding becomes better, and that's why we are doing this. So the frequency, so mu L initially when you apply the static magnetic field B naught, this is the Larmor frequency. Now when we apply this radio frequency, this B1 is being experienced by the nucleus, the magnetic nucleus. So the precessional motion that we just saw in the video is now happening like this. The magnetization vector will be moving along this circle, along this cone, in fact, along the B1. So B1 के अराउंड वो सारा मूवमेंट होगा. वो जो B1 एरो दिख रहा है ना y एक्सिस में, xy प्लेन में, उसके अराउंड M, कैपिटल M मूव करने लगेगा, viewing from the rotating frame of reference when you have a circularly polarized. So the second precession that we are talking about will be given by, in the same manner, gamma b1 by 2 pi. So initially the this was your precessional frequency in the when it was moving along the applied magnetic field b naught. Now when the magnetization vector starts also moving around, precessing around this b1 vector, the frequency is given by this. So the two frequencies are equal. If they are equal, then the absorption happens, energy transfer will happen. So things will have so called rotating frame. So we have just discussed these things. Now this pulse is we are talking, we should also understand the time duration of the pulse, how we talk about the different types of pulses that is applied in such a system. So usually, so as I told you, mu uh, so duration of, if pi by 2 gamma b1, if this is the pulse duration, it can be defined in this way. So frequency means that you are completing one. So what does this mean? Gamma 2 pi b naught. This means that it, in a complete rotation in 1 second, happens in this much time. In complete rotation, sorry, there are this much number of rotation per second. So one rotation takes gamma b naught. That's the time frame. Okay. So this, what does this mean? This means one rotation 2 pi takes one complete rotation gamma b naught seconds. One complete rotation is gamma b naught. So in a similar fashion, you can understand that if we write pi by 2 gamma b1, that means it is not going completing its rotation. It is only moving by 90 degrees. So one complete rotation means going by a 360 degree. If I write pi by 2 gamma b1, so this is, we are talking about this second precessional frequency. B1 is the radio uh, magnetic field vector of the radio wave. So pi by 2 gamma b1 is the time when the magnetization vector decreases. It moves by in the circle by 90 degree. Okay, and then we say that we have, if we do that, then we say that we have applied a 90-degree pulse, or we say that we have applied a pi by 2 pulse. Usually this comes out to be on the order of few microseconds. Okay, so 90-degree pulse means that this vector, you started from here and you are only moving up to this. So you're coming from here to here, it is 90-degree. So the magnetization vector, which was a sum of several magnetic momenta of all the nuclei present, angular momenta of all the nuclear momenta, then you calculate the magnetic moment from that. That is the capital M, gives you capital M. Okay. So 90-degree so when we say we have applied a 90-degree pulse, we mean that this around the B1, the when it starts moving, the magnetization vector starts moving, and it has moved by 90 degree in this frame, and then we stop. So the duration is very short in that sense. If you say that you applied an 180-degree pulse, that means the magnetization vector will completely oppose to it. It will be here, and you have moved from this to this. So this will be a 180-degree pulse. So you understand the difference. And when you say that a 360-degree pulse, then nothing is changed, the complete rotation. So you are not actually doing anything. So mainly you will find that application 360-degree pulse it means nothing. It means you are not it is not useful in the real sense. So these things are analysis of is useful when you vary the pulse duration, 90-degree pulse or 180-degree pulse. So it also means the spins have inverted. When you apply 180-degree pulse, it also means that all the alpha spins which were pointing up, the पूरा का पूरा कोण उलट गया है, सब नीचे आ गए हैं सारे के सारे. 180-degree pulse का मतलब है, और 90-degree pulse का मतलब है कि वो आधे पे half. So this also means what does this, एक और चीज जो आपको इंटरेस्टिंग है, ध्यान दीजिएगा, प्लीज ध्यान दीजिएगा. When it is here, alpha states more in number, more populated, that's what we say. And when you are, if the magnetization vector is pointing like this, it is the beta. Most of the beta state, if M is like this, is the beta states more populated. Beta state is more populated, that is the way we say. Or you can say that if you have 100 nuclei, if all 95 were pointing up in the previous case, that was this vector, and now if it is the vector is completely M, if it is moves like this, then we have most of it, the 95% of them are almost in the beta state, the pointing downwards. The Z component is pointing downwards. That's the M that we are talking about. So if we are application of a 180-degree pulse means that the magnetization vector is totally reversed. Its direction changes completely. By that logic, it is easy to understand what happens to a 90-degree pulse. A 90-degree pulse means when you apply that radio frequency for that much period, that short period, for that particular duration, you will achieve a population where alpha is equal to beta. In terms of population, the population of alpha and beta states are population is equal. So alpha state and beta state, in terms of their population, they are equal. So if you had started with 100 nuclei, each one having random alpha and beta orientation, so now they once magnetic field was applied, they were aligned. Most of them were aligned with the field, and you are having the magnetic field M, capital M. And now when you apply 90 degrees pulse, it has become equal. Alpha and beta population are equal. Alpha is more in number, beta. So this is the difference that we understand. Okay. So coming back, discard the whole thing and then start again all over. Okay. So yeah. So this is what we mean by applying a 90-degree pulse. So initially, if you have alpha state was more populated, you have more individual momenta of, if you look at the individual nuclei, most of the angular momentum was pointing, having the Z component pointing along plus half, having plus half. Now when you apply 90 degrees pulse, the population becomes equal. The plus half and minus half, the alpha and beta, become equal. And when you apply a 180-degree pulse, the magnetization vector is totally reversed. It changes direction. So the population is now more for beta and less for alpha. So this is the idea, and as I told you, it usually this comes pulse duration. If you calculate, it comes out in microsecond. So this was the thing that we were viewing so far in a rotating frame. अब आप फिर से वापस आ जाइए, वो बड़े वाले सर्कल, नीचे वाले सर्कल पे बैठ गए थे ना, उससे बाहर निकल जाइए, तो फिर हम वापस एक एक्सटर्नल ऑब्जर्वर बन जाते हैं। और अब हमको वो सिग्नल डिटेक्ट करना है। वी हैव टू डिटेक्ट समथिंग, फाइंड सम वे टू, ये सब जो चेंजेस हो रहा है ना, इसको ऑब्जर्व करने का तरीका नहीं। सो आई एम कमिंग आउट ऑफ दिस rotating frame, become an external observer. We go to the laboratory frame, stationary frame, and now what, we apply a coil, detecting coil. So it is, if you have read magnetism in 11th 12th classes, you know, solenoid and all those things. So this is a coil which can, where you can induce a current, a signal will be generated. And so what happens that if you are in a rotating, coming out of the rotating frame as an external observer, you will observe that the magnetization vector is moving in this circle at the mu frequency mu L, and this will induce oscillations, coil, a signal in the coil, rotating frame induces a signal which is oscillating signal. It will be same as having the Larmor frequency of the system that we are discussing. So this usually, so, and then this detection coil is attached to your computer system, and you get this on the spectrum. There is Fourier transformation algorithm, and you get the spectrum right away on the screen. So that is easier said than done. So the processing is done. Next is the processing of that signal that is done, and it is done by subtraction of the high frequency signal, so that you can only analyze the that is generated signal induced oscillation in this coil. So that is detected, and it is usually comes out in the few kilohertz. So that is the thing. So there is this. So initially, we had all the we have a large number of spins, all were aligned. Capital M was the magnetization vector for some when we carried out summation of all these individual magnetic moments. Moments नहीं momenta होना चाहिए. Momenta is the plural of moment. Okay, so इंडिविजुअल्स. सो अभी तो सारा जो एक साथ ऊपर मूव कर रहा था, अब वो धीरे धीरे समय पल्स हटा दिया आपने. सो क्या होगा? इट विल नाउ स्टार्ट फॉलिंग. मतलब सारा का सारा जो वेक्टर्स. सो इनिशियली मैग्नेटाइजेशन वेक्टर वाज large, capital M. This will become so this will become smaller with time. Time t is equal to 0, t is equal to 1. Then it will fall further small, and then 0, like this. So magnetization vector M will go on decreasing in some manner. So this is what we expect, and this decrease happens in a exponential way, which is given by time constant t2. And so gradually in this detector coil, the signal will become weaker, and finally 0. So the pattern. So uh, so this is what is happening, Tn, and finally it is going to 0. So the magnetization vector is going to, once you, so after a few microseconds the pulse is gone, and there will be a decrease in the magnetization value gradually in an exponential manner. So it will oscillate. It will decrease. It is under, of course the M is oscillating, and it is the oscillation frequency, the that value of M, the vector, will decrease gradually. So let me just rub it off to have the ideas conveyed. So oscillating, decaying, free induction. So what we call this is oscillating, decaying. Oscillations gradually decay. So the amplitude of the vector goes on decreasing, the magnitude, and it is happens in an exponential manner like this. You see. So this is the decay of the signal gradually with decreasing amplitude. So you have M. So this was your value that we were talking about, M, and now it becomes small, this. So signal, if you look at it, you can look at it this way also, the magnetization vector. So it corresponds, the decrease in the signal corresponds to the decrease in the uh, uh, magnetization value of the original molecule through which it has passed, through the nuclei through which it has passed. So this is what we do observe. So it is the y component, the xy plane. We got to know that there is. So it is the y component that decreases. Okay. So because we saw that in xy plane it was moving. So you see all the coordinates we have already discussed. Initially it was precessing around z. Now the green. So remember what we are talking about. Yes. Sorry, this one. See the green one. Blue color arrow is the b naught along z. The green color arrow b1 is in the xy plane along y axis actually. So that is the y component that we are talking about, along the component along the b1. If you have a y component, so see the component along. So this is what we are talking about. This goes on decreasing. Once the pulse is removed, that will happen. So it will the y component decreases, and y component will decrease with the frequency. So the way it will decrease is like this. The green vector in that GIF you saw that green thing coming out of the, that was B1 in the Y along Y axis, and so this was having a precession around that, so that Y component goes on decreasing, Y component of the magnetization vector, uh, whatever it was. So if m naught is the original magnetization vector that you had, m naught is the max, so you can think of maximum value of t when at t is 0, when initially this e to the power 0 will be equal to 1, and so my is having maximum value. So you have cos 0 will also, it will be equal to m naught the maximum value, and as t increases, as the time increases, gradually if observed with time, this will my goes on decreases, sorry, decreases in an exponential fashion. So exponential decay you can trace out like this. You can see, if you take this the only the crests, if you look at the crest only and connect the dots, are you seeing an exponential decay? Yes. So this is an exponential decay profile, right? This is what we mean, that it decays exponentially. The y component decays exponentially, and t2 with a time constant t2. So when t is equal to t2, okay, so you can extrapolate this as, if t is equal to t2, what will happen? Signal decay 1 by e times the original value at t. So that's what is happening. So this is this way you can also define the time constant t2, what we mean by t2. We'll further understand more on that relaxation, so how why m changes. Yeah. So we have how much? So uh, so we have considered Larmor frequency of the original. When we apply B naught, the static field, it starts processing with a frequency that is Larmor frequency mu L, and now we also considered that the pulse that is being applied, the radio frequency, has an oscillation that is nearly almost the same, exactly the same. So that was the initial discussion that we started with, that it matches with that. But it has been found that even if it is just close to that frequency, it may not be exactly matching, and that is the off resonance condition. Even in that case, you can get the things, the signal. Short pulse will certainly contain, so because the pulse contains several resonance frequencies, so it is still possible. Mm, so this is the equation that we have just discussed, that how the decrease happens exponential way, and this decrease is the same. This is again a similar thing what we obtain in a, when we strike a bell, gradually the frequencies decrease. It is, so this was a single, when we consider a single nuclei having a one type of environment, this is a clean uh, profile, very neat profile that you are getting, very simple profile of exponential decay that you are getting. But in actual sense, when you have a molecule, you will have two such, at least two such nuclei, like a AX system. And even if we so for for simplicity we assume that there is no spin-spin coupling between the two A and X spins, and we apply the still we will get at least two signals which will be uh, mixed together and appear as a pulse. When we apply 90-degree pulse, we will get, there will be two different magnetization vectors corresponding to A, corresponding to X spins in AX system, and both will appear at different frequencies. So, and the signal that will be generated will be a mixture of these two waves. Okay, so the pulse profile will be different. The signal that we will get in the coil, detector coil, the so this FID curve will look like something like, so see, it has been distorted now. जैसे ही हमने दो को मिक्स कर दिया, अजीब सा कुछ पैटर्न थोड़ा, और सोचिए कि एक मॉलिक्यूल में ऐसे कई सारे सिस्टम हो, एक मॉलिक्यूल में कई सारे ऐसे न्यूक्लियस होंगे जो कि सब अपना अपना अलग सबका फ्रीक्वेंसी होगा, और पल्स जब हम अप्लाई करेंगे तो वैसे जो फाइनली जो आउटकम होगा डिटेक्टर कॉइल में जो सिग्नल मिलेगा वो ये सारे सबके करस्पॉन्डिंग जो ऑसिलेशन है, सारे एक या ऑसिलेशन x2 x3 अगर होगा सबका होगा. So the pulse profile will become more and more complicated, and this pulse profile which you are getting signal uh, versus time, it contains all the information about the vibrations of the oscillation of the two nuclei A and X. So that has to be, that is what is important to you, that is what you want to know, and so this must be deconvoluted by through a method called Fourier transformation. Fourier transformation. So see, signal versus time, it was a time domain thing, and now you are getting a signal in and frequency here. So this is the frequency domain thing which is, it is being converted, that is you are able to resolve the mixture, the pulse which was containing 2 3 4 5 and many more waves together in one pulse. Now you are able to segregate them, you are able to resolve them into two components, or if the components are more, you have to do that all the way. You will have to resolve into components, analyze it, and get the data in this form. So this is something that is what we have, I have been telling all along, that it is when you strike a bell and you hear a clang, a sound which is a mixture composed of all the frequencies that the bell can vibrate. Similarly here, when you have a molecule, and if depending on if in one molecule how many um, mm, nuclei are magnetically active, you will have all these frequencies put together in that short pulse, and it will look very complex. The pulse profile will change and you have to analyze it, get it into the form where you have signal versus time, and that is your Fourier transformation. The mathematics comes to your rescue. It helps you convert this signal into a frequency versus, sorry, this intensity versus frequency. So that is something done by Fourier transformation. So mathematical part of Fourier transformation, I'm not going into that. So this is the transformation that we were showing in figure A and B. So the A nucleus has one Larmor frequency, the X nucleus has another Larmor frequency. So we were getting oscillations for due to the each of the magnetization vector will have, corresponding to A nucleus we will have one set of oscillation, corresponding to X we will have another set of oscillation. So each one of them giving rise to two different waves. So the mixture of which appears in the overall signal, which was deconvoluted to this. Now this is what we call as FID curve. uh, okay, FID curve, uh, and the FID curve of a typical example, we are going back to the ethanol, CH3 CH2 OH. So the real thing, an ethanol, so in a molecule such as ethanol, where you have uh, 6 protons, which all of them are magnetically active, how what kind of pulse profile will be there? This is the pulse profile that you will get from a NMR signal when you use an NMR thing. And so this, it is the intensity versus time, and the intensity of all the radio waves that is present. So this is the FID curve, time domain. And after Fourier transformation, you get it in terms of frequency. So frequency, difference of frequency gives you the chemical shift, so it is still the frequency domain thing. So this is how the spectrum is obtained. Giving example of ethanol, which is the simplest one that we can think of for this discussion. This is the pulse profile, and from that pulse profile we are able to obtain the spectrum, NMR spectrum, like this. Okay, so what does this mean? This is a very complicated pulse that we have got. Why? Because there were 8 different, so 1 2 3 3 4, 3 plus 4 plus 1s, 8, total of 8, total 8 different frequencies. 8 different frequencies are there. Frequencies, Larmor. So 8 different Larmor frequencies are there. So all of them giving rise, superposed over one over the other, giving rise to this pulse profile. So this mixture of the different waves, radio waves, has to be separated through Fourier transformation, and then we get this kind of spectrum. So it looks very complicated, and as the molecule becomes bigger, you have more such interactions. You will have you need to separate well all of them. So 8 different Larmor frequencies were there in the molecule, and so you had such a difficult time. If you literally do it on your own, you will have a tough time resolving them. So each one of them, so there were 8 components, each having characteristic frequencies, and that's why this FID curve looks so complex. So but this is the normal way nowadays how we do it. This is the way we perform the spectroscopy for molecules. Okay, uh, so I think we can talk about relaxation, spin relaxation, in the next class. So that will be important. So you have learnt about the how a pulsed NMR is conducted, how it is resolved into components, the basic idea of the precessions, the Larmor precision. So we got to know about 2 different Larmor frequencies, one precession along B naught, about the B naught, another precession that happens due to the B1, that is the part of radio frequency wave. And so we'll start this tomorrow, relaxation, and then we'll like to finish after spin relaxation. Yeah. So that's all for